Hi, everyone. Um, yeah, it's nice to be here. Thank everyone for attending. Um, so the topic for today, or the topic I'm going to talk on, is DSAs in software systems. Um, and I came all the way from Dublin because of how important I think this topic is. So I hope you enjoy it. So my name is Ayo. I'm an occasional writer. I manage Twitter Spaces on Twitter. My handle is Alternate Wolf, and I'm an SRE at Google. Disclaimer: I do not represent Google in this conference, so the things I say are my opinions. Thank you. So introduction. The topic for today, like I said, is DSAs in software systems, and DSAs is short form for data structures and algorithms. And for the sake of this conversation, for the sake of this talk, I want to define them. So a data structure is a structure that helps us save data in a particular way in computer's memory. So for example, you have arrays, you have your tree, you have linked lists, you have graphs, and so on and so forth. And an algorithm is a finite sequence of instructions that basically tells the computer to do something, right? So you have the instructions take an input and then they produce an output. Now, in one sense, everything that you would ever write as a software engineer is an algorithm. So for example, all of the code you write to open and close your databases, all of the code you write to handle errors, all of the code you write to perform crude operations, those are algorithms. But that's not what I'm focusing on in this talk. In this talk, the algorithms I'll be talking about are the ones that have been well researched to solve a particular problem, like binary search. So binary search is an algorithm that helps you search through a sorted collection efficiently. So one motivation for this talk is sometimes I have conversations with people and I talk to them about data structures and algorithms, and they don't think it is important to learn, right? They don't think that it's something they should commit time to because they don't need it in their jobs. And I think that you really do. I think that DSAs are super important. And one way to, show people how important it is by talking about it practically. And so in this talk, I want to tell some stories about ways I've applied data structures and algorithms, ways I've seen DSAs also applied in different systems. And I want to focus it around 3 themes. And so the first theme is I'm going to focus on DSAs as a tool to solve problems directly. I'm going to focus on DSAs as a way to reason about existing systems. And then I'm going to focus on DSAs as a tool for novelty. So the first one, DSAs as a tool to solve problems directly. So 2 years ago, I was in a team of people that built a recruitment platform for a nonprofit. So basically what this nonprofit does is they partner with companies, and then the nonprofit interviews candidates for the companies. Now, as you would expect, the interview process has multiple stages, and these were the requirements that we had. So we needed to be able to create stages, create as many stages as we wanted. We also needed to be able to move candidates from one stage to another stage successfully. Once they were successful in one stage, they needed to be moved to the next stage automatically. It needed to be possible to create a new stage if it was needed during the process. And we also needed to be able to delete a stage. Now, I solved this problem using a linked list. I actually wrote code for a linked list. And I want to show you how the interview stage and a linked list, what the parallel is. So in a linked list, when you have a node, the node contains data, and then it also contains a pointer to the next node. And so you have a chain of nodes in a linked list. And for the interview stages, you also have the data for the current interview stage and the pointer to the next interview stage. And so you can create an interview stage like this where there are 2 stages, and the first stage contains its data and a pointer to the second stage, right? So say we have these stages, right? So one of the operations I said, one of the requirements I mentioned was we wanted to be able to insert, create a new stage. And so if we wanted to create a new stage, we would just change the pointers from, so let's say we wanted to create a stage called stage 1.5. We would change the pointer from stage 1 to stop pointing to stage 2 and point to stage 1.5, and then the pointer for stage 1.5 to point to stage 2. Now, this is exactly how you would insert a new node in the middle of a linked list. And so one big lesson for me there was that, my knowledge about a linked list, like the pre-knowledge I had, helped me, because I knew about a linked list, when I found out what the requirements were for the recruitment platform, I was able to directly apply, know that the way that a linked list stores data is the perfect model for this problem. And so I was able to use a linked list to solve that problem. Now, the second story I want to tell is about expression evaluation. So recently, I've been interested in, how can we build a program that, helps us evaluate mathematical expressions. So yeah, in a mathematical expression, you know that we need to take precedence into consideration. So for example, you see that example expression there, 2 plus 3 times 5 raised to the power 2. The power needs to be done first because power has the highest precedence in this expression. The multiplication needs to be done next before the addition. So how can we build a program where a user can give a string, this mathematical string, into that program and the program returns the right result? I found that if you represent the expression as a tree, then you can just solve the problem using post-data traversal. And so I would explain how that works. So this would be the tree of that expression. You can see that 5 raised to the power 2 is at the bottom. And so in a post-data traversal, what you do is you solve the deepest nodes first. And so if we solved 5 raised to the power 2, we would get 25. If we solved 25 times 3, we would get 75. If we solved 2 plus 75, we get 77. And so because I was able to model the problem as a tree, then the actual algorithm to solve the problem was super straightforward. And so, my question is this: if you do not know about data structures, right, how do you know what structure can correctly model your problem, right? So the second theme I want to talk about is DSAs as a way to reason about existing systems. So in this theme, I'm generally talking about, times when I have seen a feature in an app or, I don't know, use some software, and I've thought about how does this software implement this particular feature, and how my knowledge of data structure and algorithms helped me understand, or gave me a starting point at least. So in Dublin, I use an app called Revolut, and Revolut is a fintech application. So basically, you can transfer money from one person to the other, and you can also do stuff like make payments and so on and so forth. So on Revolut, when you want to transfer money to somebody, you need to insert the person's account number, and you also need to insert the person's first name and last name. Now, what Revolut does is it matches the first name and last name you enter to the first name and last name they have saved internally for the account number. If the first name and last name do not match, they tell you you can't transfer. You need to get the right first and last name. If the first name and last name match, you can transfer. It allows you go on. But I found out there was a middle ground, and I found this out by mistake. So one time I was trying to transfer to myself, and I entered Ayomide instead of Ayomide, and Revolut told me, this is a close match. Did you mean Ayomide? And I thought this was interesting. How does Revolut know that the string I entered is close to the one that they have stored? And I remember the class of algorithms that are called fuzzy string matching algorithms. And fuzzy string matching algorithms are basically a class of algorithms that tell you how closely one string matches to another one. And it basically does this by telling you how many inserts you need to make into one string to make it equal to the other one, how many deletes do you need to make, how many replacements do you need to make. So in this example, if I wanted to find out how close kitting was to sitting, a fuzzy string matching algorithms would tell me, I need to replace K with S, I need to replace E with I, and I need to insert a G. So those are 3 operations. And so a fuzzy string matching algorithms would tell me, I need to carry out 3 operations to make the strings equal. And so in my context, I can now decide in my app if 3 operations means that these strings are close, right? So I do not know that this is exactly what Revolut does, but it gave me a starting point to think about it. Yeah. And so, the second example I have in this case is, I guess, something that is more relatable. So Spotify's music player. So I'm sure a lot of people use Spotify or Apple Music. I think it works for both. On Spotify, when you open a song, you can add songs to a queue. Now, wherever you see queue, I want you to think linked list, because a queue is really a linked list in disguise. So you can add a song to a linked list. And so if I add a couple of songs to the queue, I can represent them as a linked list like this. And so I can model the queue on Spotify's music player as a linked list in this way. And so if I want to, when you add a new song on Spotify's music player to the queue, it gets added to the back of the queue, like it to get added to the tail of a linked list. And if you want to play the next song, it gets removed from the top of the queue, like it gets removed from the head of a linked list. And so that gave me like a model to kind of think about how Spotify might have applied that. But I have a question for you, and like whoever is able to kind of give me an answer for this, I have like something for you. I'd ask like afterwards, after my talk. So on Spotify, you know that you can rearrange songs, right? So you can take a song from any point in the queue and move it up if you want. You can make it second and so on and so forth. You can also delete a song from any point in the queue if you wanted. Deleting and replacement. So if you want to delete a node in a linked list and you want to replace a node in a linked list, those are really slow. So you need something else, in addition to a linked list to correctly solve that problem to make it fast. Like, how can you do that? So that's my question. I'll ask afterwards. Cool. So the third theme and final theme is DSAs as a tool for novelty. And in this one, if you're like on tech Twitter, you would have seen, I don't know, tweets at some point about, people talking about why should I invert a binary tree in my interview if I'm never going to apply it to in my real job, right? I'm sure people have seen this from time to time. And generally, these jokes are funny, but I think that sometimes there's a propensity to kind of glaze over what is really important. And I want to draw your attention to something. If you actually took the time to learn how to invert a binary tree, you learn about pointers and you learn about recursion. And pointers and recursion are things that you would use as a software engineer at some point in your career. These are important things. And so one argument I have for why you should study, really take data structures seriously, data structures and algorithms seriously is, as you solve problems, as you study, you're able to learn concepts like pointers, you're able to learn about things like recursion in a low impact setting. You're not, there's no money to be lost at that point. There's no data to be lost at that point. You have a problem you need to solve, and you're able to take your time and learn it. And so I think that if you study data structures and algorithms, you're able to learn those concepts in your time properly, so that when you do need it on the job, you might not need to invert a binary tree, but you need a pointer at some point, right? And so taking the time to do this study would give you a critical foundation, and there would come a time where you need to solve a problem that Stack Overflow can help you with, right? And data structures and algorithms as a foundation would help you think creatively, in those situations. And so we have a few examples. I'm sure a lot of people here might know my friend Emmanuel Bakare. So Emmanuel built a tool for databases, for a disaster recovery tool for databases that is based on MapReduce. I don't know if people know what MapReduce is, but MapReduce is a technique that is based on a class of algorithms called divide and conquer. And so the creator of MapReduce had an understanding of divide and conquer, and they were able to create a technique that had never been created before. And this has also enabled Emmanuel, my friend, to create a disaster recovery tool that didn't exist before. And so these are questions that you can't really find on the internet. And I think that DSAs as a foundation would help you create things like this. Yeah, thank you.